Hello, my name is Anna Jarman. I am a sophomore studying math here at Carroll, and today I'm going to be presenting on the CBP-LSS Resource Allocation project. So this project was completed during my time as an intern at Pacific Northwest National Lab in Richland, Washington. I started my internship during the middle of this project, so I'm just going to give a little bit of background before I start talking about my work. And this background, happened prior to my involvement in the project, but is important to understanding the project as a whole. So CBP-LSS stands for the Laboratories and Scientific Services Division of Customs and Border Protection. They have labs across the country that deal with processing suspected controlled substances, especially those crossing the border. And at these labs, they have a demand for more efficient processing of the samples that they do receive. So they came to PNNL with various information about their labs, the number of chemists that each lab's had, the samples each lab saw per day, and the items each lab saw per day. And just as a quick note, the current number of chemists at each lab has been redacted throughout the presentation for security reasons. But anyway, CBP-LSS came to PNNL with the hope of getting back optimal numbers of chemists to assign to each of their 8 labs so that they would increase their processing efficiency of these samples. So just to take a quick step back, I mentioned this is a resource allocation project, and for those who maybe aren't familiar with that term, resource allocation basically means, we have some resources that we want to deploy. In this case, we want to assign chemists to work at 8 labs across the country for Customs and Border Protection. But we have limited resources to deploy. So in this case, there's only a certain number of chemists employed by the entire system of Customs and Border Protection. And so we want to find a way to assign these resources to different places so that overall system risk, the overall risk for the entire thing is reduced. And risk is, in this case, is how we quantify how efficient these labs are at processing the samples they receive. So high risk is correlated with, in this case, low efficiency at processing these materials. And so we could, guess and check and, assign chemists places and then see how efficient we're doing, and we could play around with it that way. But we could also use tools to help us run optimization algorithms. And so in this case, the optimization tool that was most frequently utilized was Excel Solver, because then we can use Excel Solver to tell us where we want to send and assign our chemists to best benefit the entire system that we have. So our basic methodology with this project was first to simulate process flow at these 8 labs because we didn't receive historical data on their processing efficiency, so we wanted to simulate it, and then use that data from the simulation to formulate system risk, again, which quantifies how efficient the overall system is at processing. And then from there to perform an optimization algorithm to minimize the overall system risk by changing how many chemists are assigned to each of the 8 labs. So again, prior to my involvement in this project, a discrete event simulation was run using the ARENA software that models actual process flow at each lab for each of 5 defined demand levels, which were defined based on the mean samples each lab saw per day. And then we also ran the simulation for they ran the simulation for different numbers of chemists assigned to each lab. And so the measurement that was taken from this simulation was the percentage of samples in the simulation that took greater than 45 days to process. So basically the proportion of samples that took too long, in a sense. And so here's just an example from the simulation. This is just for one lab, the San Francisco lab, for 5 different demand levels, where the probability that a sample will take greater than 45 days to process is shown as a function of the number of chemists who are working at that lab. And as you can see, as the chemists go up, it takes less samples take a long time to process. And just to take a quick step back, basically, I mentioned that Excel Solver was used as one of the main optimization tools in this project, so I just wanted to explain a little bit about how optimization with Excel Solver works. So with Solver, we have an objective function, which is a function whose output we want to minimize or maximize by changing the decision variables, which are the inputs to the function. And then we might have constraints, which are limiting factors on the objective function or decision variables or both. And these are passed into an optimization algorithm using Solver. And then we basically are left with the optimal decision variables to optimize the objective function. So the Excel Solver was actually used twice for optimization as two different tools. So the first job of Solver was fitting a model to the simulation data, which was shown in a previous slide, so that we could begin to formulate overall system risk. So I was given data, this simulation data, and asked to fit a model to it. So I decided to use Solver. And so the way Solver worked in this case was the objective function was a sum of squared residuals, which just quantifies how different the model is from the data. So we wanted to make that as small as possible because we wanted the model to fit as closely to the data as possible. Then the decision variables were a and b in this function f of x because the simulation data was determined to have a functional form of a reverse sigmoid curve. So we wanted to find the optimal a and b such that our model most fit our data. We had no constraints. We passed this into the GRG nonlinear method, which basically looks at the gradient of a function when its partial derivatives are equal to 0. And then we found the optimal variables, or in this case coefficients, a and b, such that we had the closest model for the data that we were trying to model. And so I ran this for every lab and every demand level. So each of 8 labs, each of 5 demand levels, to find optimal model, to find the best model for each scenario, basically. And so from there, we were able to formulate system risk as the sum of the risk at each lab, and individual risk at each lab was just the probability that a sample would take longer than 45 days to process. So the f of x in the equation shown in the previous slide. And so we defined total system risk as the sum of all of those. We defined the objective function, which we would use in our optimization as kind of a transformed version of this for numerical stability for when we ran the algorithm. And so then we could calculate, for example, the current risk of the overall system at medium demand level for each lab. So if we look at, for example, the Chicago lab, we have our A and B for the Chicago lab at the medium demand level, and we have the current number of chemists, which is X, at the Chicago lab. And then we plug those into our function that we have to get the risk of the Chicago lab, and then we can do that for each lab and add them up to get the total system risk, and we can do the same thing for the objective function. So then came the second job of Excel Solver in this project was to minimize system risk by changing the number of chemists assigned to each lab. So again, resource allocation. So basically initially, different combinations of demand levels and total numbers of chemists were run to find optimal resource and chemist allocation. However, there were only the combinations of Python only explored a few different numbers of total chemists and 3 of the 5 total demand levels, because to run all of the combinations possible, that would amount to about almost 4 million combinations, which was too many to run in Python. So we decided to find a way to automate Solver using Visual Basic for Excel to create a user-friendly tool that would run specific combinations that a user wanted to try out if it wasn't already included in the Python optimization that was run. So a user could come into this tool and say, oh, I choose the medium-high demand level for certain labs, which wasn't included in the Python optimization. So what is my optimal chemist assignment at each lab now? And so the first task in creating this tool was to set up Excel Solver again to be used for resource allocation. So in this case, our objective function was the overall system risk, which we wanted to minimize. Our decision variables were the number of chemists assigned to each lab. Then we had constraints on chemists, including the total number of chemists that were available for assignment, because we have a limited number of those. Again, we used the GRG nonlinear method, and then we were left with the optimal chemist assignment to each lab in order to minimize system risk. And so from there, we were able to create this Excel tool for the user. And so basically how it works is the user will input, okay, I want this demand for this lab, this demand for this lab, and so on for each of the 8 labs. They would input a total number of chemists that are available to assign across all 8 labs. And then from there, the Visual Basic Excel programming would basically take over. So there would be a separate results table that held combinations that were already run in this tool specifically, so that a user wouldn't have to run Solver, or so that Excel wouldn't have to run Solver if a user had already decided they wanted to explore that combination before. So Excel would run a binary search through this results table of combinations run already. If Excel found the combination that had already been run in this tool, then it would display those results from that combination. If not, it would call on Solver to optimize the specific scenario that the user wanted to look at, record those optimization results in the table for future use, and then display those optimization results to the user. So here's just a dashboard of the tool. So the target profile shows that you can choose the demand level for each lab and the total number of chemists, and then the user would hit re-optimize, and the optimal number of chemists that they should assign to each lab would show up along with some risk calculations. And so in conclusion, based on the Python and Excel optimizations that were both run, we were able to provide CBP-LSS with the optimal chemist assignment to each of their 8 labs, which involved moving some chemists around, obviously, in their system. And then we could look at the original system risk as defined and calculated in a previous slide, along with the risk after the chemists were reassigned. As you can see, it went down. Other than that, it's a little difficult to think practically about this because risk is defined as a sum of probabilities. So we can also look at the risk buy down, or how much the risk was reduced, which is about 22%. This is still a little difficult to kind of practically think about, but I think it gives a better idea of how the risk has changed. And so this project now allows for a risk-based staff assignment system across CBP-LSS labs that will hopefully increase their effectiveness at processing potentially illicit materials. I'd like to acknowledge Customs and Border Protection and Laboratories and Scientific Services, along with Dr. Wendt, who's my research mentor at Carroll, and along with the group at PNNL that I worked with on this project. Thank you.